Hello, chemistry students. Today's lesson, we're going to go over section 2 of chapter 4, structure of the nuclear atom. We're going to talk about the three types of subatomic particles, which I'm sure you've been hearing since, middle school for sure. But we're going to talk about them in a little bit more detail, so pay attention. And then we're going to describe the structure of the atoms according to the Rutherford atomic model. And you'll learn what that means. So to begin with, those subatomic particles, and again, you've heard over and over and over again, you talk about it every year in science, the protons, neutrons, and electrons. So those protons are the positively charged particles in the nucleus of an atom. Neutrons are the neutral particles, and electrons are the negatively charged particles surrounding the nucleus of an atom. But the protons themselves actually determine the identity of the atom. What that means is, for example, all atoms that have 8 protons are always oxygen. All atoms that have, 7 protons are nitrogen. Everything with 6 protons is carbon. So if I take a carbon atom and I somehow magically get another proton to stick to it, let's say I'm trying to, invent a new element. If I take carbon itself and make another proton stick somehow, I have not made a new element because an element with 7 protons already existed. And in fact, I just said that that's actually what nitrogen is. So if we look at the periodic table and how the elements are arranged in order of atomic number, they're really arranged in the order of the number of protons that they have. So the number of protons actually, again, gives an element its identity. The neutrons, we kind of know that they contribute to mass because we talked about that in the last chapter, but obviously they have a job other than just, contributing to mass. Neutrons provide something called nuclear, and that is not how you spell nuclear forces. Nuclear forces help hold the nucleus together. If you think of, we always talk about how opposites are attracted. So in ions, when we learned about ionic bonding, I'm sure you talked about it in quick physical science, we review it a little bit in biology, those opposite charges attract. So positive charges are always attracted to negative charges. So why in the world would a whole bunch of positive charges in the nucleus of an atom stick together? Well, they wouldn't. If you tried to put a whole bunch of protons together and make a little nucleus out of it, they literally would repel each other, and the nucleus itself would just kind of explode in all different directions. What the neutrons provide is kind of a buffer between those positively charged protons. So the nucleus of an atom would not stay together were it not for those neutrons. So sometimes they're kind of like the forgotten, or we don't contribute a lot to the neutrons, but they're really important and they have to be there in order for that atom to exist. The electrons, we know that they're these negatively charged particles that surround the nucleus. The electrons themselves determine the reactivity of an element. And that will make more sense when we talk about the arrangement of different electron shells. But why isn't that going away? There we go. But ideally, the electrons have everything to do with what things will react with a particular element, how reactive an element is, or how non-reactive an element is. So the electrons give it all of those chemical properties that are associated with an atom. So they're very, very important. Even though they're super tiny, they really don't contribute to the mass of an atom at all, but they're very important. An electron is a negative charge is equal to a proton's positive charge. That's why elements on the periodic table have equal numbers of protons and electrons. Those charges cancel out. So a proton is a charge of +1 and an electron is a charge of -1. And remember I mentioned yesterday, how do we know that these tiny little particles exist? We really can't see them. Well, there's lots and lots of experiments that have been done that indicate that this must be the structure of an atom. We can't see it, but there's lots of research and experiments that have been done that can't disprove this. So this is the widely accepted atomic theory, that we have those particles. And honestly, we're going to spend a little time talking about the research that has been done that indicates these particles exist. So this really brilliant English physicist named J.J. Thomson, in 1897, using something called a cathode ray tube. So this is just a tube filled with gas that has a positive end and a negative end on the tube. So there's a positive end and a negative end. Yep, this is the negative end because this is the anode. And honestly, I have a super cool video. I don't think you'll be able to hear the sound on the video. So this is the cathode ray tube, and it's just a short little one. I don't think you're going to be able to hear the
inside. It's actually a vacuum tube.
The audio that goes
so there's
with
nothing
it.
but a vacuum on the inside, and it's called the cathode ray tube because this is the anode and this is the cathode. Right. When it's hooked up, it doesn't do this.
So what he's doing is he is subjecting it to a charge, and he can make, so there's a gas tube that he's running a current through, and if he subjects the beam to a charge, he can manipulate it. And what J.J. Thomson realized was that if he subjected this tube to a negative charge, it would repel away from, oops, I got to stop this because it'll just play again. So J.J. Thomson, figured out that if he has this tube filled with gas and he runs a current through it, the gas will actually glow and he'll see kind of a beam of light. And he wondered, what is that beam of light made up of? Well, he then discovered if he put a charge at that beam, if he actually put a negative charge on this near the glass tube, it caused this beam of light to deflect away from the negative charge. If he applied a positive charge, it caused the beam of light to move toward the positive charge. And so knowing that opposites attract and like things repel, he then concluded that the beam must be made of negatively charged particles. And he is actually the person that proved the existence of negatively charged particles, or those electrons, just because of that behavior of that beam. Why would that beam behave any differently? It was repelled by negative charges, so it must be a negatively charged beam. Oh, look at Miss Benson has a typo, that all electrons have a specific charge. I do want you to jot these down. Pause if you have to. So he proved the existence of the negative charges, but we had no idea where they were in the atom. So they did believe that there were atoms, obviously, by this time. Well, he came up with something called the plum pudding model. He's like, they must be like, apparently plum pudding is an English thing. And he said, well, they must be just sort of interspersed throughout the atom, like raisins or like plums in pudding. Sort of like chocolate chips in chocolate chip cookie dough. Think of it that way. So just dispersed throughout. He really had no idea how they were arranged in there. And he didn't have any way to find out using these methods. And then to build on J.J. Thomson's work, Robert Millikan, a U.S. physicist, using tiny little droplets of oil suspended between two charged plates. He got them to basically stay suspended between two charged plates. He actually used that method to come up with the actual charge of each electron, and also the mass of each electron. So we say that an electron is 1,840th the mass of a hydrogen atom. And remember, hydrogen is just one proton and one electron. This is why I say it takes almost 2,000 electrons to equal the mass of one proton. And then right around that same time, or sometime after J.J. Thomson's discovery, Eugene Goldstein observed that that same cathode ray tube, he also found some particles that were traveling in the opposite direction. Now remember, electrons, those negatively charged particles, are going to be traveling toward the positive end, right? Because they're negatively charged, and we're running that current through. We said there was a positive end and a negative end on our little cathode ray tube. So the electrons are moving toward the positive end. But he found some moving in the opposite direction, and he said, hey, there must be some positive particles also in that cathode ray tube. So that's the first person to say, hey, there's some little plus particles in there as well. And then James Chadwick, 1932, whenever I see the 1900s, I always think, well, that's not that long ago, because I'm old. He confirmed the existence of neutrons in order to explain the mass of the atom. By this time they were working on finding the mass of atoms, and they realized, oh my gosh, well, if we can count the number of protons, and we know what the mass is, then something's missing, right? Like it just doesn't make sense. And he said, apparently there's these neutral particles that aren't charged at all that contribute to that mass. So now we've talked about the existence of those electrons and how J.J. Thomson discovered that, how we came up with the fact that there's, protons, those positively charged particles, and also the neutrons. But we still really didn't know the structure of the atom. And how in the world do you figure out the structure of something that you can't see? Well, Ernest Rutherford of New Zealand is credited with that very act. His famed gold foil experiment. And I feel like you guys probably talked about at least a couple of these in ninth grade physical science when you talked about the history of chemistry. He had this really interesting device that he set up. So we knew at this time that the atom was mostly empty space. Okay, so they're like, oh, there's a lot of empty space. So if I fire positively charged particles at a thin gold foil that's literally one atom thick, these tiny little charged particles should go right through, just like if you were throwing marbles at a volleyball net. You would expect that they would go right through, okay? And that's what everybody expected. But guess what? Some of them didn't. A few of them, well, and he kind of thought, well, some of them will get deflected a little bit because they might hit the edge of something. Just like if you threw marbles at a volleyball net, some of the marbles might get a little bit deflected because they might actually hit a string. But you wouldn't expect them to be deflected a lot, right? What he found, though, is some of them bounced completely straight back, as if they hit something solid and dense. And this is where he's like, oh my goodness, there must be a dense, solid part of an atom, and that's actually what we call the nucleus. So just really in a nutshell, this is kind of how Rutherford set up his experiment. So he had a radioactive source that gave off alpha particles. Here's a super thin piece of gold foil, and then he had a detector shield built up around this. And he thought he would see particles hitting here, maybe some here, maybe some even as far over as here. What he did not expect were particles hitting that super thin gold foil and not going through at all. Like that was completely unexpected by everyone at the time. So the only conclusion could be that there's a nucleus, and that's actually the three particles.